has on me.
Yeah.
I'll only have to boot 6 times though.
Okay.
I will know what the problem is if it does.
Right.
So,
All right.
your entertainment. This is tricky because I got a highly menu. When I miss at 5K, miss one of these corners, it goes behind and I have to get it this way. Which, thank you. May or may not need. Oh, I don't know.
Yeah.
Okay. So I was struggling a little bit to get going.
Yeah.
Because I've given it a configuration pretty good solid work. So this is like nice minus 10. And then when it finishes, you get to see for the dual 22 cores. So that's 44 cores plus 44 hyperthreads. So that's 88 guys there.
Yeah.
Trick 50.
Yes.
First thing you notice, you hit carry turn and nothing happens for a second.
Right.
50 is okay. Seems to be doing a little better than the nice whatever I had. So I picked like 5 of these. Each one has a different. See, narrower.
Yeah.
You know why that's narrower?
That's spotted against time, right?
Yeah. It took exactly the same time. We both hit the same frame rate. It's narrower because Church stole cycles from this history plot. Yeah. It stole about half the cycle, so it cut this width in half. Okay. Anyway, so I have some fun books.
So the video processing spent more time, more actual time.
All of these are limited by something. CPU or data movement.
Right.
Each one has got a different. This one is triple. This is the highest.
UUASC node.
Mostly, yeah. Except for you guys. Hey, if you want to fill out a job application, maybe we can work something out.
I was actually laid off last Tuesday.
Oh, actually the mic's live. But hey, no worries, dude.
I don't really actually care.
Yeah. Well, yeah, before you get to the emotional side. Huh?
Is there anybody on the team?
I don't know. I don't think so.
But we are.
But it's, oh no, there's 4 viewers, so yeah. But hey, maybe they're looking to hire you as well. So. But I figured I'd turn the mic up. Because maybe Shinji could do some of his demo now.
How good you Russian?
Yeah, hey Shinji. No, you guys hang out over here. Let's gather around. Hey, warm your hands.
There you go. It's don't use a band for it.
So hey, everybody, this is Shinji Nakamura, and I hope Nakamoto. I hope that he's doing a quick demo of his work in progress, 5-node Ceph cluster running on Raspberry Pi. Take it away, Shinji. Why don't you tell us about what we got going here? What's making the lights blink?
So basically, this is a 5-node Raspberry Pi Ceph cluster. Yes, you could run Ceph in like Vagrant or VirtualBox or whatnot. But I thought this would be a fun way to work with Ceph on physical hardware. The whole build cost about maybe somewhere a little south of $400 to do. But yeah, afterwards you have a 5-node cluster. 1 node is the monitor. 1 node is the S3 gateway.
Oh, hey, there was a question. What is Ceph?
Oh, okay. Ceph is a software-defined, object-based storage solution.
Distributed
Storage solution. So the idea is you take a bunch of commodity hardware, you install Ceph on it, and you have a resilient storage solution.
that can serve.
So the base file system for Ceph is a object storage system. That's just the base. You don't necessarily directly access it. So for client access, Ceph provides 3 modules. One of them is called CephFS, and it's analogous to NFS. Another one is called RBD, and it's analogous to SAM storage or block-based storage. So you would mount an RBD image, kind of like a hard drive on whatever your client is. The third one is Rados Gateway, and it's analogous to, everyone's probably familiar with Amazon S3. So HTTP-based object storage. So when you build a Ceph cluster, you have all 3 access methods available to you. One thing to note though is that you can't access the same data all 3 ways. It's you write it through one method, you access it through the same method. Any other questions about Ceph?
And basically, and you can handle, since it's a distributed thing, you can handle failure of a node and still serve data.
Exactly. It's the whole Ceph product is based around consistency and high availability. One thing to note about Ceph, if anyone's familiar with other software-defined storage solutions, I'm only familiar somewhat with Gluster. A limitation of other software-defined storage solutions is that there's kind of like this one node or one node type that's responsible for keeping track of all the data, like a bitmap or whatever you want to call it, and you access the cluster through that node type. So it effectively becomes the bottleneck of the cluster. Ceph was kind of unique in that the name node, the monitor node, only keeps track of what's available, And when your client accesses the cluster, it accesses all the data nodes in parallel directly. It doesn't have to go through this name node concept. So it's more massively parallel compared to previous solutions.
So I think you nailed the Ceph stuff. So tell us a little bit more about the hardware. Looks pretty cool.
So this is Raspberry Pi 3s. They're gigahertz processors, 1 gig of memory. Unfortunately, it's 100 megabit Ethernet.
Oh, 100 meg.
Yeah,
Not even giggy.
no, not even gig. So that's kind of the bottleneck in my current cluster. For this one, I've used Samsung 32 gig USB drives for holding the data. And it's basically 3 data nodes, 1 monitor node, and 1 S3 gateway client.
Cool. So this is really work in progress. Hopefully we can have you back to do a more formal display. But since you had this thing in your pocket on the way over to the meetup, I figured it was worth doing a quick demo.
Yeah, and it's, again, you can do this with virtualization and get the same effect, but it's kind of nice to be able to work with physical hardware, be able to pull out thumb drives and simulate disk failures easily,
Right.
And look at like the architecture, see where the bottlenecks are, and plan out your cluster. And it's Ceph today, I wipe it out. It's Hadoop tomorrow, and I wipe it out.
OpenStack.
Yeah, OpenStack. Bill suggested Elasticsearch.
Yes.
What OS are you running?
So I am running Ubuntu because it was the path of least resistance to getting Ceph working. With the Raspberry Pi 3s, you've got to run Ubuntu 16.04. It's got a little bit of a problem with heat. It runs pretty hot. I actually usually have a fan running on it.
Okay.
But yeah, there's Raspbian and other OSs available too if you want to do that. Any other questions? No? All right. Thank you guys.
Hey, thank you, Sheik. So hopefully we'll have him back soon for the full demo. So I guess we can just hang out for a little bit. I'll come back, I'll do an intro. In the meantime, there's food and drink and various chatter. And actually, if you want to take a look at Gary's awesome 5K display and 22-core system while we're hanging out, waiting for other people to show up, that's cool. But in the meantime, I will mute the mic so we can speak candidly. Okay, and then hopefully, yeah, we get a level here. All right. So, hey, yeah, everybody, hey, yeah, we're getting started here. So let me, I'm going to do an intro, and then I'll call you.
Take a mic.
Okay.
So it works.
Let me make sure. Let's bring up the slides as well. Okay. Hey, welcome everybody to the October 2016 Unix User Association of Southern California, Los Angeles chapter meeting. Thanks everybody for attending. My name is Jordan Schwartz. I book the presentations for the LA chapter and always looking for more speakers. This evening, Gary Demos will be doing his presentation on Linux real-time software imaging. And also, he'll be doing a presentation first, and then he'll retreat to his most awesome 22-core system and 5K 27-inch display to show us some imaging, real-time imaging examples in real time. But before that, I'd like to just talk about some Unix User Association meeting business. So UUASC, I guess first question is, I guess to be a member of the Unix User Association of Southern California, all you got to do is join our mailing list. How many folks are either new and or not on the UUASC mailing list? Show of hands. Okay, just a couple. So if you go to uuasc.org, there's some stuff about joining our mailing list. So please join. We actually have 3 mailing lists. One is the main mailing list. So that's just for general discussion of Unix, Linux related topics, and or beer. So please join that. There's also one called UUAC-announce. That's just for announcements of upcoming meetups or something that's terribly interesting to the group, but what have you. And then finally, there's one called UUAC Jobs. That is for Linux or Unix related jobs in the Southern California area. And that could be either A, you have a job to present, or you're actually looking for work. And you can post a link to your resume or what have you. Or just announce that, hey, I'm on the market, I'm looking for work. Give me something. So subscribe to at least the main list and the other lists if you're interested. Also on the UUAC jobs list, it is a moderated list, but you don't need to be a member to join. So say if there is some recruiter type that is hounding you for this most awesome position that's maybe not the best fit for you, but it is a Linux or Unix related job here in Southern California, you can post them to, hey, go to uuasc-jobs@uuasc.org. Just send your thing over there and the moderator will look at it, validate it, and pass it on through. So it's a good way to get the word out. So that's it for the mailing list. Please join. We meet, the LA chapter meets somewhere in LA, usually on the west side, on the first, ideally on the first Thursday of the month, but you know, occasionally I'll just push it out depending on availability and other issues. I like to meet here at Verizon Digital Media Services, and I'd like to thank the folks at Verizon Digital Media Services for providing this facility, the food, and the drink, because it is quite awesome. So, yeah. And of course, Verizon Digital Media Services providing a full service of I guess, content delivery and video services, and they're always looking for skilled engineers to help build out that network and provide those services and solutions. So you can go to the Verizon Digital Media Services.com website, and then also Cameron here is a recruiter. And also made sure that the kegerator was fully loaded, so you can come by and thank him for that, and also talk to him about potential opportunities working here. This is one of the bigger shops here at Silicon Beach. We're doing a heavy Linux implementations in many data centers around the world, and getting those systems deployed in an automated fashion and serving content in a very competitive environment is quite a challenge. So there's a lot of interesting work to do in various aspects here. So, and Cameron can tell you about some of the opportunities that are there. So once again, thank you, Cameron. Back to UUASC stuff. We try to meet once a month, first Thursday of the month, usually here, because it's very convenient for me. And I'm always looking for speakers. So if you're interested in presenting at UUASC, please email me at you can email me. I post up on the list, or you can email me at leaders@uuasc.org, and you just tell me a brief sentence or two about what you'd like to talk about, what have you. If you don't think you have a full presentation, I can maybe pair up a few short ones with some other short pieces. You know, we can do the lightning talk type theme. But I'm always looking for presenters. Also, and if you're looking just to attend, definitely make sure you're tuned into the Meetup site. You know, the meetup.com site is the best place, you know, to get the up-to-date information on what's happening. I'll also email out to the mailing list, but meetup.com site has been a very valuable asset for communicating out. And then, as you know, we are live streaming this event. By the way, I guess I should point the camera my way. We're live streaming this event these days via the Google Hangouts on Air, so that I get a decent recording. So if you can't make it, try and check the, you know, if you can't attend in person, try and check the live stream, or at some time shifted after the fact. I guess other announcements. Oh, for one thing, I guess we do have a little, Cameron left us a nice little jug, a little cooler to keep your favorite cold drink on the desk, or maybe take something from the kegerator home. I don't know how we're going to raffle this off, but it's here. That would be cool. And let's see. I guess we're. Oh, go ahead.
We need to get somebody to rewrite the directions to get here.
Okay.
How confusing that was. I've been here twice and I still couldn't.
Okay. Well, perhaps you can contribute some prose. At the Meetup site, there's a little comment section. If you've got a better description, I'll take it. I thought it was pretty good, but I guess not. But the punchline is, well, whatever. So and if you just get here early, the food gets here early anyway. So your reward, if you get here early, you'll definitely get a nice Mendocino Farm sandwich, and the keg won't be won't be run out by that time. So yeah, I guess get here early if you do plan to attend. But apologies for the confusion. It is a little tricky. But you should know, you've been here like 5 times already. This shouldn't be an issue. So maybe there's some other issues there, but yeah, we'll write it. Yeah. Okay. Also, I guess does anybody else host meetups or anything like that? Does anybody have any announcements they need to make? The one other thing to bring up, and this also plays into presenting here at UUASC, is SCALE. The Southern California Linux Expo for 2017 is booked. It's official, going to be in Pasadena again at the Pasadena Civic Center or whatever in March. And Sean has a question.
So I actually helped run SCALE, but Call for Papers is ending at the end of the month. So
Dude, Call for Papers is ending at the end of the month. Get your submission in now. Then also send a copy to me, and maybe we can work you in. You can pre-present here at UUASC, work out the kinks, then you get to the big show, and you kill it. Yeah. So, but see the call. So go to, what is it? Linux SCALE.
if you type in SCALE into Google
And Linux. Yeah.
No,
Really?
SCALE.
Okay.
It's first link. Like, you gotta Google
Just
images,
put scale in your browser there at home, and then click on call for paper, submit
Just
something.
understand that A is not capitalized, so type that in, you definitely get it.
Okay. Don't capitalize the A. So yeah, scale is coming up, and UUAC is a good place to flesh out your presentation before presenting there. So I guess, also I'd like to thank Alexi at Vertical Sysadmin, that guy there, because I think he helped bring Gary in here and now. So with no further ado, it is the return of Gary Demos. Take it away.
These work, right?
No, I haven't even tried. The crowd can hear you. So there is a microphone here for the live stream. Yeah, don't need it. I'll try and get it working.
I know how to do the right and left arrow, so I think.
Here, I might have to log back in. Hold on. Pardon me. Oh,
no,
you're good to go.
Okay. All right, so a bunch of stuff about me. I think the kind of the key point in that was that my company Demographics, which I had for 14 years. Oops, where'd the picture go?
Oh, sorry.
It's on this screen, but not on that screen.
Huh.
Plug that guy out.
Maybe I knocked the line out.
There we go.
Pardon me.
We came out of screen mode. Okay. Is my last company was sold to Dolby in 2003. So I've been kind of working out of my own house since then. But before then, I figured in order to do what I wanted to do, I had to raise money and put big computers together and stuff. So my first machine was at USC in '67, a 360-44, which is sort of between a mainframe and a mini computer. And for that and that point of time and about 10 years thereafter, computers were made out of things that looked like refrigerator-sized stuff. That was that, and even the mini ones, that just means not very many refrigerators. There was a PDP-10 at Caltech. I came back to that later. Down the street here, there was a company on Slauson, down by the Fox Hills Mall, called Information International. Anybody here ever heard of that company? Several people. Okay.
Whoa.
So it was right down the street here, and they had PDP-10s and what they call III-15s, which were their version of a PDP-15, 18-bit machine. PDP-10 was a 36-bit machine. Some of the early machines, they said, well, gee, the memory that so-and-so is making in cores is 18 bits, so we'll make our machine 18 bits, without any further thought as to why that would be a good or a bad idea. I got down to some pretty neat stuff after III, a company called Digital Productions. We had a Cray 1S and an XMP. We had a VAX as a front end. That was a 32-bit and a 64-bit machine. And then a connection machine, CM2 eventually. We were the first delivery of a CM2 that was 16,000 processor cores in the SIMD configuration with 2,000 Waytech floating point chips. So it was really massively parallel. And it was a lot of fun. You program it in Lisp. So here we are with, count them, 6 refrigerators, I guess, 7. In those days, some of you know that here, but in those days, machines were only intimidated if you had a beard. So
Oh, that's where the Unix beard came into
they
play.
would not obey you unless you came to work with a beard. Well, isn't that right? Still true. Yeah, that's right.
And you still have to run a Unix variant, right, to intimidate these systems.
I believe so. Yes. Frank Crow, Jim Blinn, John Whitney Jr., Carl Brandt, John Whitney Sr., Art Durinsky, and yours truly.
Wow.
John and I with the Cray, that was our XMP, about 1984. Notice that refrigerators became other kinds of household furniture. You could sit on it. There's some kind of couch. And this was the first CM2. That was all of the Thinking Machines company in Boston.
Wow.
And me and my guy, Jim Hardy, in the front row there. So after the big machines, we started looking at some other ones. SGI had this wonderful Linux IRIX, and there was some kind of nice Linux Unix in IBM as well. So the RS-6000s and such, and some other machines around. There was a bit of a battle between GL and PEX and some other kinds of graphic system. The GL that's ubiquitous now there was a period of time when it was one of several contenders. So that was an interesting shakeout. I always ended up on the losing team, and then had to go to GL when it ended up winning. Also worked with another massively parallel machine called a MassPar. Now nowadays, you know, GPUs for a few $100s that you put in your PCI slot in your computer are massively parallel things, and you program them with OpenCL. So all that kind of big machine parallelism kind of came back, except that the model for execution kind of kept changing around. So what I have over here is a dual 22 core. It's known, I think it's a Broadwell E or EP or EX or something. It's 22 cores, hyper-threaded. This is dual 22, so with the hyper-threads, there are 88 processing active things. So that's getting, you know, at least moderately parallel by itself. And they're SIMD. They have AVX2 and 32 bits, that's at least 4 things, and 8 things are probably coming in some generation, although.
What is SIMD?
Single instruction, multiple data.
Ah,
I have taught you something.
Thank
You didn't
you.
know that.
I learned something new today,
So
Quota.
MMX and then AltiVec and these things, and about 20 years ago, when you'd issue one instruction and it would do 4 multiplies or 4 adds, that's SIMD. And on those machines I was talking about, it would do 2,000 or 16,000 things.
Wow.
And in these modern GPUs, the high-end NVIDIAs and AMDs, it's doing thousands again, 3,000, 5,000. This is 3,000, I think, in this GPU. This is an NVIDIA Titan X. Okay, so yeah, it's neither of those two, but those are powerful performance too. AMD FirePro W9100 and NVIDIA M6000. The M stands for, I forget, Maxwell. And now this one is a P, which is for Pascal, I think. And I use the GNU compiler because I trust it to make a binary that runs, but I use the Intel compiler if I can get it to work because it makes a faster binary on these Intel processors. So what I'll be showing you here in the demo afterwards is running. It was compiled and runs on the code made by the Intel compiler. It was this code's kind of complicated, and it took a really long time before the Intel compiler would actually make running code for any piece of what I was doing. But eventually they got there, and then I finally am a subscriber, and I actually do the updates and get the upgrades. And it gets about 0.5% better every time they do a release every 3 months or something. So it's kind of neat. And it's a good 10-15% faster than GNU, although GCC gets faster as well. This display here is 5120 pixels wide by 2880, which on a 27-inch display isn't really big enough. It needs to be a kind of a bigger display. And it's done as 2 sections, 2560 wide by 2880 tall. And they sync up. So it's got 2 display ports coming out of the GPU. This is running Scientific Linux 6.7. I was running on my laptop 14.10 until yesterday it said, oh, gee, we're not supporting 14.10 anymore. You need to come up to 15.04 or something, and the graphics driver went crazy. And so I got to rebuild the system. I was going to bring it and show it, but anyway, I'm also running on Ubuntu if I can get the driver and the version of the OS happily compared. And I'm used to Yum for updates. Ubuntu apt-get, it's a more complicated world for me. I'm just not used to it, I think, is part of it. Any of you apt-get experts, I praise you. And help. I didn't go that far, but I thought about it. So that was the laptop. It's a 38, it's only slightly bigger than these Macs. 3840 by 2160, so it's really fine pixel pitch. But I normally run it at half that and just do the GPU's onboard upsize because it doesn't have enough computes to really play that at speed. I have trouble with permissions on Ubuntu. I don't seem to have those on Scientific Linux. You know, I'll write a USB thumb drive. It'll all be fine. I'll bring it back on my Scientific Linux. It's all fine. I take it to Ubuntu, and all the permissions are wrong. Huh. And Alexa just told me how to do a -R on the CH mod, so I don't have to. Recursive. I haven't tried it yet, though. We'll see. I have tried these other Linuxes, and now I'm trying to get to something. Probably, I think, Lexi, you're saying 16.04 is what I should aim at. Yes. Because it's the long-term stable. The 14.10 that I've been on was about a year. So the long-term means something, and the long-term release, the long-term stable or whatever that is, LTS.
Yeah, it's the even 04 releases.
The 04. So
even years.
But only the 10 and the 14. The 1404 wouldn't run the driver, so
yeah.
I ended up stuck. I'm going to show you a demonstration of priority and scheduling. There have been Linux versions that have special kernels, real-time kernels, and there are still to this day some kind of descendants of those which you can patch. Now, kernel patching is a little bit beyond my skill level, but if I had Alexi behind me, I would be brave and proceed ahead. But without him, I'm a little bit timid. But the NICE is pretty much ubiquitous. I don't think there's any system, Linux system, that doesn't run NICE with whatever scheduler it's using that's a Linux or a Unix. But churd, I don't know how ubiquitous it is. It certainly runs on 1410 because I could watch its behavior, and I will demonstrate these. And churd also has a choice of schedulers, although I couldn't see much difference in them. I could see a tiny amount of difference. There's a round robin, there's a FIFO, and whatever the default one, and I read about it, it was kind of sophisticated. It runs pretty well, so I've not been suffering from the choice of scheduler. But if you say churd, anywhere from 1 to 99, you get different behavior. The scheduler that runs with NICE is not the scheduler that runs with churd. And if you run NICE and churd together, the churd dominates. So it's useful to think about it. And you'll be able to see a distinction between hyper-threaded processes or running things and non-hyper-threaded, because they'll in some of these they'll bifurcate. You'll get two bands of activity. One's more busy than the other, because the hyper-threading is if I'm not busy, go do that. If the cache is, if I stall out on memory. Oh yes, and messing with the either NICE or churd, but especially churd, can really make things bad, and I will demonstrate that. Let's see. From code level, there's some other things you can do. So, but just from the command line, these are pretty accessible. There's some other stuff you can get at, and some of these I've tried and forgotten, and some of them I haven't tried. But you can actually query some things and set some things. Proc sys kernel is some kind of virtual limited you guys know about these things more than I do, but it's some way of setting system parameters that makes it look like a file system, but it's actually not. It's somewhere in the global running world. These things are interesting to mess with, and they can affect stuff. And what was the thing you said, Alexei, about there were groups of control groups? So in a political year, we don't go into too much detail about control groups, but that's something else. Apparently we can lock processes to processors and other interesting things. So there might be some interesting things to try in that. The config preempt, that's the real-time kernel patch that I was talking about. It's a preemptive scheduler. A certain amount of time goes by, and it says the important process gets the cycles now. I don't care what else you think you're doing, it goes there. And those, the ones I've tested, which were pre-built, worked pretty well. But I'm not really brave about patching kernels. But I'm brave about rebuilding the system when I destroy it that way. So you will see a demonstration where there's some smooth motion in there. It's not perfectly smooth if you look at it carefully. It's trying to be perfectly smooth. The display is running at 60 refresh, and it's going to update at, it's going to try for some of those at 30 and some at 24. And every once in a while, it might get one extra of the 60th. You might see it, you know, but in the end, it will have made the speed and kept the time that it says. It'll tell the frames per second. But it's got a couple of buffers in the GPU and a couple in the CPU, and they're all interlocked with semaphores and shared memory and DMAs up to the PCI. And what you really want is something different. You want a different architecture than what is available with what we have here. And I haven't been able to get this to happen yet, but it's been in the background on my to-do list for about 7 or 8 years now. I have a board in here made by a company called DVS out of Hanover, Germany. And what they do is you send them frames, and they just accept them. And when their number of frames that they can hold is about half full, so let's say 10 frames, you say, start playing. And then you just try and keep that thing from ever getting starved. It's a big FIFO, a FIFO of frames. And that plays perfectly smoothly. You can gen lock it, you can do professional broadcast. It doesn't suffer from this. I'm going to the screen at 60 and I'm playing at 24, and where am I going to take up the slack that those don't go into each other? Now there's a cross interrupt. See if I have that. Am I on the right world here? What's this forward? Okay, that's forward. Well, okay, that was forward, but it doesn't show what I was thinking of. So this system has CPU processors. There are multiple processes done with fork. Semaphores between them to say when frames are ready, and to a display process which manages the DMA up to the GPU. Once it gets to the GPU runs OpenCL on it, and that talks to GL, and GL lets it put the pixels on the screen, and that's called CL-GL interrupt. CL is computer language, I guess. OpenCL, it's what CUDA migrated into by Apple's efforts. It's the programming language that's fairly strong, that's device independent, that runs on GPUs and CPUs, and as SIMD oriented. So what you could make this FIFO idea if you had an interlock between GL and CL, so that you could make the frames, a bunch of them, start the thing going, and get the interrupts and get the communication all happening and keep it from collapsing. The GPUs have 12 gig, 16 gig, they have an unbelievable amount of DDR5 memory, and some of them even have this stacked vertical memory. So there's plenty of memory there to have a big, long FIFO of frames. And you could fill up 3 frames and then start it and then just keep filling it, and you'd never start. You'd always be perfectly synced up. Now, there's a get sync from GL to CL, and there's a get sync from CL to GL. You only, I think, need one of those. And I think one of them works, but last time when I was working on this, none of them worked. I tried both of them on any brand of GPU. So this is a kind of a work in progress. Is how do I get all this stuff functioning, software in CL/GL land? And the names are pretty arcane for what these get the cross syncs are. But if you go hunting, you'll be able to figure it out. It's in the GL documentation and CL documentation for at least 3 years now. It just hasn't actually functioned. Okay, so another issue for me is what I'm going to be showing you on the screen over here is decoding. It's essentially decompressing. If you buy a DVD and put it in your DVD player, it's decompressing MPEG-2 in real time. That's what's happening. It's an integer compression codec. What's going to be running in software here is a floating point compression codec for high dynamic range, high precision. It uses a file and folder structure. So there's a folder for each resolution layer. If there's motion compensation, there's a folder for the motion compensation vectors. And there's a basic header information that it reads once when it starts or anytime things change. And so it goes into the folders and reads files for each resolution layer to make up to 5K in the case of what I'm showing you here. So this file reading, why would I want to do that? Well, if you take MPEG-2, which is what's on your DVD, or similar codecs, it's what they call a multiplex. It's got whatever you're going to see in one version only. So if you want layers of resolution, you don't want a multiplex because it has to be frozen. I think of a multiplex as what you make at decode time for a specific incarnation. So it's in files and folders so that it can be flexible at decode time. So if I'm coming in over a network, I can go to a lower resolution, eat less network bandwidth, and still get a nice picture. Now there's a problem if what I have in there for my bits files in the folders is SATA 3, I guess it is, SSD. It's a Samsung 2 terabyte. And what kind of format do I want on that? And I can actually decode real time from a thumb drive. But if you put NTFS in there or HFS or something, every time it goes and gets one of these files, it's going to put a stamp. It says, this was last accessed at so-and-so. So it does all this writing. Well, I'm decoding. I don't want to write on every file. And Lexi knows, because I was beating my head against this for a number of years. There's a process that hides in the system called flush, which pushes out all these writes. And the flush process was messing me up in my real-time decode. So I figured all this out eventually, and I figured out that ext2, I mean, if you build a modern Linux, you'll get ext4. But ext2 had the ability to do a read-only mount -R. It's just in the mount command. You can put all that stuff up there. No update of the access time.
No A time, which is the no access time.
Yeah.
That's what's, it's keeping those metadata rights that you don't need out of the way.
I should have listened to him when we first met.
Oh,
It would have saved me a lot
I
of
only
trouble.
see because you got it on the screen.
I do now.
Yeah.
But I found that it took a really long time for me to find it. A simple mount command, you plug in the thumb drive in the ext2 format, you unmount it, you remount it. And that lets you play real time off a thumb drive in my file folder.
That's why your presentation is so interesting to us Linux Unix users, because you're really taxing some things that maybe we don't drive that hard. for you, issues with the Linux scheduler is an issue, and even Linux file system mount options, right? You don't get the right options, you're not having any fun. So
Real time is real time. The audio is real time. The picture's real time. If it's not all working real time, it's no good. So it's a hard constraint, if you will.
yeah.
So not every thumb drive will keep time even if you don't do that update. So I tried a number of brands. The ones that rated well on the internet, about half of those actually would play. So I got several of the ones that played well, and then like nice little 128 gig. They're very specific, and they were pretty good on the internet of saying which ones actually did the job and which didn't. So it was kind of fun. Now there's an issue with flash memory. The stuff wears out. You write and read a bunch of times, and the glue gets mushy.
The cells get used.
They get tired. I don't know.
Yeah.
I don't know what the right verbiage is. But something goes bad, and you have to say, okay, I got to move that data over here while I can still see it. If you do this, that won't happen. So every once in a while, every 100 plays or something, you have to let it play once without all this, just with a normal mount. And it will go and move everybody around, because the -R will prevent it from doing those repairs, the read-only.
But yeah, because
it's a right.
It's
a right when you move things. Okay. Sync. Have any of you been typing along, giving shell commands and said SYNC carriage return? He does. 2 of you. Okay. Four. Okay.
I did it back in the olden days before running halt, but yes.
So what sync does? So what did you say?
There you go.
Well, there you go. And what were you gonna say? Okay, so what it does is it says, okay, quiesce everything. Now, some configurations of Linux stuff do pre-read heads, pre-fetches. You started doing something and it says, well, he's going to be doing more of that. I'll just do it in case. So when your program stops, you finish the movie or you stopped it or whatever, it may be busy. So if you say sync, when it returns from sync, it will have stopped all that kind of stuff. So I put syncs between each show, if you will, because that means when I start it, I don't have a mystery startup. And I also put sleeps and timers and things between, since I fork a bunch of processes and I do semaphores and make shared memory and I interlock it all, I do little delays and stuff just so that everything is in a known state when it fires up. Because if you don't do that, there's so many combinatorics that you can start yourself up into a lock. And some of the locks mean a reboot, just like the old days. Okay.
Just run sync before you reboot.
Among other things. But the locks, it isn't just sync. The locks,
Oh, yeah, no joke.
semaphores in a Mac OS, the semaphores are killed when your top process is killed. Automatically.
Parent.
The parent. Over here in Linux, I kill the top process, all the semaphores are still sitting there. Next time I start it, I run out of semaphores.
Good deal.
My man, don't leave without talking to me. I need to know how to do that. That's important to me, anyway. Yeah, I couldn't figure it out. So what I do is I quiesce everything and then I trap it all and then I delete all the semaphores. But if I miss the trap or I get into a case where the file reader fails instead of my code, I didn't trap it, and then it's a mess, and I got to go clean them all. Okay. Let's see. So just general file systems. I take disks between Macs, and I won't admit the PC Windows stuff. and
you.
Linux machines.
Thank you.
And the only file system that I found consistently on the Linux versions that I was using that I can interoperate is NTFS, but it's very poor in terms of performance. ext2 actually runs reasonably well with the Mac. I have no idea about that other. Raw is in write blocks to the device. Since I'm talking to flash memory, I'm afraid about the flash update stuff. I don't know if that interacts with the ext2
so
and NTFS, but I'm worried that it might.
My guess is when the flash is reassigning blocks behind the scenes, the addresses that you're calling, whenever you call block 1 or block 2, it's giving you the latest, the real version, the version that you would expect.
I hope
But
so.
you know, you'd have to experiment.
I don't know. I mean, there's a long history of people making a cheap device and kicking off to a driver's behavior somewhere that's implicit, that they don't tell you and you can't find out. I should take you seriously, though.
But the other one.
But ext2 is pretty minimal.
Well, looking at the other one that's not up there is XFS. And here at Verizon Digital Media Services in our Edgecast content delivery network, we use a lot of XFS for performance.
A big one? Oh, for performance.
Yeah,
it's
well,
not a big guy like NTFS.
No, it's performance, unlike NTFS.
Okay.
It's an extent-based file system. So that might be another place to look at. Maybe I can ask around.
Jim's here remembering all this for me.
Yeah,
and
thank
Lexi,
you, Jim.
they will remind me. That's very good. That's why I like coming here. I'm talking to the right guys.
And also, ZFS, although it's not really designed for performance, you can disable the no A time, and could maybe work too. That's kind of solving different problems.
Yeah, I was glad to find the ext2 that I could actually do.
Yeah, no,
find any path that works, but I got to replace NTFS. It's just a dog.
Thank you. Yeah, that's great.
And EXFAT, which is also FAT64, is just not ubiquitous enough on Linux version. It's on some, it's not on others. It's read on some. Okay, so a key ingredient for me, I'm with 88 runnable execution threads. Lightweight threading is a valuable commodity. I can throw out 300 threads, and the scheduler is lightweight enough in threads that it won't bog it down measurably, a couple percent maybe. So it's really very, very strong. And that's, I think, hardware and microcode or whatever the modern version is. That's Intel's really hard effort, and presumably AMD's as well. The OpenCL I have mentioned. It has been really valuable to me. Before that was CUDA and shader language and things which were tough to know precision. The transcendentals were not robust. There were lots of things that were really disturbing. The OpenCL spec, even from 1.0, specified the LSBs that you would get from every transcendental function, square root, power, it tells you the rounding. And that really, really is a big difference because you know what you're dealing with. If you went on the GPU before OpenCL, each GPU would give you different number of good bits, and especially in floating point. Pretty difficult to work with. Now I use macros. I probably shouldn't. Anybody here going to scold me for using macros instead of functions? I mean, you have every right to. He's brave. He's right. I deserve it. When you're coding along and you see something, you're going to run it several times. If you just put the backslashes on the end of it and do a pound define, you can invoke it all over the place. It doesn't do any argument checking. You're asking for trouble. You're an evil person like me. And he's right. He's going to the good place. So But there's an advantage, at least there was for a while. I was able to take the macros, if I didn't put any SIMD instructions in them, and include them in OpenCL code as well as in multi-threaded CPU code. And that became really, really handy as a practical matter. Now, eventually, OpenCL supported functions, so it will check the argument types and all the important stuff that functions need to do. But in practice, it's inlining. In other words, it's doing what the macro did. There's no performance difference. So I wasn't very strongly motivated to go fix all my evil ways. But anyway, but it means I have common code that runs on the GPU and the CPU. So that's very nice. And you can do that with functions and not be evil. Okay, I think I've talked about all those other pieces. So there are timer calls. There's something called USleep. Have you heard of that? UUASC-LA. It's available in most C implementations, I think. It's microsecond accurate sleep call. It works pretty well. There are millisecond sleeps and sleeps that are very, very inconsistent. But USleep is pretty solid, I found, and it gives a pretty accurate measurement. I think it runs in clock cycles or dozens of clock cycles or something kind of amazing. So it's a real interesting thing if you haven't looked into it. And so I can say, go sleep for 0.37 milliseconds, and it will go away and come back. And
That's a quick nap.
Yeah. And it's worth $1 gazillion because he says a millisecond's worth millions nowadays. So on the network, anyway. Yeah. And he's got a beard, so we know he's telling the truth. So if my semaphores didn't kill IPCS minus S, would tell me what all the bad one is, and then I can do an IPCRM minus S for each of the 87 that I left laying around, and he's gonna fix it. Yeah, so I have to do that 133 times. Oh, I'm so disappointed. You know, there are people. Oh, wow. It'll mess up your system. There are not very many semaphores available, and so you run out of them on. I haven't been able to find how to increase that either. I did find out how to up the number of forked processes.
I know IPCS will tell you what the limit is, but I don't know if it will change it.
I think that's might be compiled to the kernel.
Yeah, well, what I do is I go take the list and I patch them, and there are people who write these little scripts that are Yak and Lex and all this, and I just don't have any of those people around me nowadays. Okay, so chmod, Alexi fixed that before we got here by looking at my slides. He says minus capital R recursive will fix that. If you do this, which you have to do on Ubuntu because the permissions are wrong, it says that, and then you have to do this, and that takes forever. So if minus R actually works the way Alexi and
Oh yeah, it's a recursive. Yeah, it'll just go down and kill them all.
Jordan says it works too. We're going to see if these people. You tried. I'll give you credit. You tried. You thought you had it almost. If any of you actually think of the automatic kill all the system symbol, I mean there are a couple of them en route. Yak and Lex. Yeah, well. Yeah, the file folder thing, you know, so I got a bunch of layers and thousands of frames and, you know.
And all of your semaphores, they had the same parent ID, right? So really, you want sort of a kill all the semaphores that were part of this parent process ID.
I want whatever Apple did on the Mac. Because anything get killed, and all the semaphores were killed automatically. You never had to go bother.
I think that's a BSD variant thing.
Yeah,
so
maybe.
Score 1 for Berkeley Systems Distribution.
Okay. So when I DMA to the GPU, so DMA is direct memory access copy. So it's a copy from the memory of the CPU, maybe over the North Bridge, maybe, you know, there's fanciness in a two-processor system, over to the PCI, up to the GPU. When that happens, it has to be in not user space anymore where I made it. It has to be in some kind of space that can go through the hardware. So usually there's a kernel copy. Well, I don't want that. So there have been several implementations. Both AMD and NVIDIA have made them, but they didn't survive long enough for me to actually make one of them work. But they came up about the same time. They both decided we better do something about this. So it's a to be done issue. My shared memory buffers and some other buffers, if I can make them in lockdown space, or if I can control the North Bridge, you know, there are a lot of things here that could help my performance by factors of 2 or more. This was this issue. Have any of you ever tried LSPCI?
Oh, yeah.
Oh yeah, okay. Well, it tells you a lot of stuff, and then if you find the thing in there that you actually cared about,
right,
it will tell you lots of interesting properties. The trickiest part about GPUs is normally they dynamically toggle between the 8 gigatransaction per second and the 5 and the whatever this other ones are, and so the speed is a little ephemeral. In other words, that doesn't really tell you. The NVIDIA control modules will sometimes show it to you and sometimes give you partial control over it. But it's generally a wandering thing. And so once you find the GPU, you do this funny thing. VVV just means verbose, verbose, verbose. It doesn't think you mean it when you only say 1 or 2 of those. And the -S is just which of the devices. And it will tell you a lot of things, not just the gigatransactions per second, but a lot of other interesting things. So that's, if you haven't done it, it's a very interesting thing to do. Am I missing a little bit of my page here? So in this machine, there are 2 PCI buses, one down here and one up here. And I have the DVS up here and I have the GPU down here. One's on one CPU's bus on its side of the North Bridge, the other's on the other CPU's bus. And you can see that in this command. You can see which of the CPUs is in charge of which device on the PCI that you have plugged in. That is unusual stuff and needs, at least for me, I need to understand more about it, but at least you can see it with that. Okay. So I tell it when I launch how many threads maximum each process is allowed to have, and then how many forked processes I want to have, and it will run them at runtime. And if I go over 32 or 31, it will say I ran out of the thing, so I have to set up the limit. It's in that Proxys kernel thing. I set the limit up to 60, so then I can launch 40 forks, and I can tell each process you can have 15 threads maximum or something. They're not always all going to be able to use that all the time, but you can actually get something big. And there's a number for fork processes times threads. That's the maximum. It's about a factor of 100 or something. You can query it in the system, bigger than I ever reached, and I'm running out of something. So, but I can up to 63 and higher. I think I've tried it higher, and certainly I can run lots of threads. But sometimes both of them, putting them up, I'm running into some limit I haven't been able to find yet. If I run a single process, which I will be doing here, I can have as many threads as I want, but I'm not forking processes. But I can be more interactive. when I had lots of forked processes, if I hit a keystroke, I have to send a message across the semaphore, an asynchronous interrupt style message to every single process, and they all have to react, and probably they would all update it. You know, it's. I never wanted to do it, so I didn't do it. So I run a single process, and that lets you have full interaction because you're just talking to that one process. Now there are two worlds for keyboard and mouse that I have run into. One is X11, which seems to be what Linux wants me to use, and the other one is GLUT, the GL User Toolkit, which is what the Mac seemed to want me to use. And there are 3 or 4 other choices, none of which I ever implemented, but seem to be offered. The X11 is the one I'm going to use here. The thing I don't like about it is if you do a Shift-S, it takes a Shift command, changes I'm in capital now, takes the S, oh, I'm in capital. You lift it up, oh, I lifted up the Shift. It doesn't just say you got a Shift S, Cap S. So it's kind of messy. I don't really like it. And there's a bunch of stuff which was on the cusp between Unicode and ASCII. So there's some 16-bit things and some 8-bit things, and they're kind of intermixed in a clumsy way. Anybody here know about any of this? No? Okay, well, anyway, there's these weird worlds about how and I have to essentially lock off the Windows and X11 and all that stuff and take over as a single window in order just to receive commands on the keyboard, because the get TTY and all those kind of things, they don't work in the modern world because it's going through USB, and you know, it's we've gone beyond it. So I interact with the display controller, and that lets me have interactive control over the GPU goings on, which are downstream of the display control, but I don't send messages back up into all the decoder processes, which would be really complicated. Okay. So TIFLib is built into some versions of Linux. Anybody encountered that? You know, you build a Linux, you got TIFLib already on there. It's in userlib. No? Okay, so there's a yes. It has some bugs in it. Beware. The TIFLib that comes installed in some Linux versions has some bugs in it. You can download TIFF over the internet. Some versions of that has some bugs in it. Beware of TIFF. It's tricky. Especially the 30-bit float representation in TIFF files. So everybody has to use TIFF to exchange stuff, very common, but it's scary. If you buy a high-end still camera, get a Canon Mark II, yeah, Canon 5D Mark II. It will make .cr2 files. I have learned from various people, including Adobe, that those are TIFF files with undocumented tags, custom to the camera. And Adobe told me, well, with this camera on, I probably can't say anymore. But anyway, somehow people find out what tags to parse, and they so that you can read a CR2 file into a Photoshop. You know, that is 2 different companies, and so those things are made to work. It's tricky. It's a tricky world we live in. The DPX file format is mainly 10-bit integers, but it's a pro format. Some of us here have used it. OpenEXR is the one I have been using mostly for the last 10 years. It's on openexr.com. There's software tools for it. It's a pretty big, complicated system, kind of like TIFF. But it seems to function. It has a nice little lossless compressor called PIZ. It has some lossy compressors. I don't touch those. The code is difficult to work with, the OpenEXR code. I have trouble with I've written my own version of it, a clean implementation of both TIFF and OpenEXR, but the people who contributed to the work with me both said, no, you cannot share that. So I know it exists because I've written it, but I can't share it. I can use it. So a clean implementation of image file formats are needed. It's a sore need, and that's why I put so much effort into it. Half float, you know what that is? No, okay. So if you go to the IEEE floating point spec, there's 32-bit and 64-bit and maybe 128-bit. There's also a 16-bit float. I think it's called float 16 maybe. The name varies, but it's also called half float as a common term for it. It was developed by NVIDIA working with the ILM visual effects group out of Lucasfilm about 15 years ago. It became instantly popular in computer graphics. You build a reflection map or a lighting model because it's high dynamic range. It also supports negative numbers, so it's good for computation. So what kind of, TIFF doesn't support that. It supports 32-bit floats, but that has bugs in it. So anyway, I've got a version of DPX that supports half floats, again, non-standard. I was the guy who founded the DPX committee in SIMP. So I feel brave enough to mess with that.
Are you including frames though in these image formats?
Well, what I'm showing here is compressed about 30 to 1. I'm using these all uncompressed. But except for PIS, which is about 2 to 1, bit exact. So there's no loss in the way I use any of these. Anyway, file formats are an issue. I just mentioned it because you probably come across these.
Yeah, so, you know, I mentioned Scale, the Southern California Linux Expo. That might be a place locally, you know, where you can talk to more people that are contributing to various open source projects. Maybe not open source image stuff, but it's definitely a good start. So hopefully we'll see you in March.
Well, we can certainly continue that discussion.
Yep,
We're in touch
I'll
on
email
email.
you.
Yeah.
Sorry, I have one more question. These libraries, have you encountered the max resolution problems yet? We don't see it handle some of these bigger megapixel images yet.
It's an issue. I haven't had trouble up to 8K, but you know, 16 bits integer. 16K is at what is that? It's 14 bits. 16K. So and 16 bits unsigned is 64K. So somewhere between 16K and 32K resolution, I expect problems. The signed bit in 16-bit integers means 15 is your maximum if you're using shorts instead of unsigned shorts for your variable. So yeah, we'll have to start watching out for that. But I haven't had the good fortune to have to go over, you know.
I'll talk to you later. I had another project that a huge image from stitching. And yeah, open source software I was using was a tip mixing out.
Yeah, cool. Very fun. Okay, so what's high dynamic range? I was reminded that the last time I presented this group 5 or 6 years ago, I showed high dynamic range. It was probably pretty early in that. Now,
Yes.
if you go to Fry's, where I went today, you can see for sale high dynamic range displays at what they call 4K, but it's usually 3840. Slightly, 15/16 of 4K to be more exact.
And iPhones can take photos with high dynamic.
And there are camera things that will use a fast and a short shutter or open the lens, or there's an iPhone with 2 different cameras at 2 different sensitivities, automatically seeing at the same time. But you know, lots of interesting ways to extend the range. But in the professional motion picture area, the high-end cameras are already high dynamic range without any of those tricks. They just make frames, whatever frame rate, 24, 60, whatever it is, and they're already high dynamic range, especially if you noise reduce on the darks, the noise floor, push down the photon.
Is it taking multiple shots, or is it doing it raw and saving different bracket values?
None. It just grabs them enough bits. The sensors are big and they're expensive, and the cameras are big and expensive. But they do a good job. The high-end cameras, the ones that Jim and I work with. Okay, so cameras have ever-widening range, just as they're coming out of the gate. They compete with each other. Some of them are incredible in low light. There's a Vericam from Panasonic. They had a set at NAB where it was almost dark enough that you couldn't see color. You know, rod vision was kicking in, and the camera was seeing a relatively low noise, full color image on the same scene you were standing there looking at. You can look at the camera, you can wiggle it, see it was live. So it's pretty amazing at both the low end and the high end. The same is true on the still cameras. Just you take a click, nothing fancy, no HDR mode, and you've got a really incredible range. Certain models are especially good at the low end or the high end or in the middle. Displays are getting brighter. This one is what the measure of screen brightness is a candela per square meter, and that it's also in English units foot lamberts, but we're moving away from that finally. But there's a vernacular for candela per square meter called nits. And so this display here has a peak white of 300 nits. When you look at it straight on, it drops off to the side or above. And so that's pretty good. Old CRT televisions were about 100, 150. The UHD sets that are HDR high dynamic range that I saw in Fry's are going in the 500 to 1100 range. And there are more coming with even more range. And the LG ones have this technology called OLED, or organic light emitting diode. And the OLED has a fabulous black. And you can recognize those LG OLEDs because they say LG OLED, but also because they have astronomy pictures where the black looks like a black sky. And they have Horsehead Nebula and star fields and things. Really impressive. So the landscape is that we have this expanding range. There's also an expanding color range in this. And I just thought 16-bit integers, which are at the core of MPEG-2 and AVC and HEVC, the codecs that are out there, Blu-rays and Ultra Blu-rays. These formats are kind of running out of precision with 16-bit signed integers as the computational engine. There are several hundred computations stacked up between the coded bits and the screen. That's enough to mean that you need more than 16 with these. So I'm running a floating point codec here. Now, high dynamic range can be harsh. If you have some really bright stuff and it flashes at you, kind of like the commercials, you know, a cut every 2 seconds or 1 second or half. I count. When there starting to be a lot of cuts, I count them. You know, there's an advertisement for the show coming later today, and they'll cut every 12 frames at 24 frames, or every half second. And I can't, I'll just close my eyes after about the first 20 cuts. I'll say I'm not watching that. I'll wait till the next commercial. So if there are starting to be warnings with these high dynamic range displays. Say danger of epileptic seizure. It's right in the manual, and there's a spec, an international spec. I think it's ISO or ITU, which says be careful about certain frame rates, and that's 15 or some years old, and it applies to cathode ray tubes. So with them getting brighter, it's even more of an issue. So if you go to a trade show, you see some bright stuff and it's uncomfortable, you'll know what's happening. They haven't mastered the aesthetic. Now, it can be beautiful. The stuff I saw in Fry's today was beautiful. They had side-by-side standard dynamic range and high dynamic, and the high was beautiful. You know, they had colors in the sky, and this guy was all washed out because there was no range for the sky brightness, and other things like that. It was just beautiful. But you can make it go wrong. So Jim and I and a bunch of people are pushing hard to try and gain control of the aesthetics.
So
Because they don't fall out. It's not natural. You have to pay attention.
So I had a question about high dynamic range, more kind of, I guess, from a layman perspective. Or in last time when you demoed HDR, you had, I guess, a 4K screen or what have you. But the advantage for one thing for a still photo taken in high dynamic range is that if the lighting wasn't right, it was too light or too dark, you have a lot of leeway to make it lighter or darker, right? By basically changing the exposure or the f-stop effectively, right? That's part of the range.
Well, you're raising a very interesting issue. If I make a high dynamic range show, what am I looking at when I make it? If I'm making it on a 500 nit display, what happens when I take it to the 1500 nit?
Yeah.
Or the 200 nit? And so that's something Jim and I are working on, and we call that single master HDR. And the way we've been doing it is to lean towards the scene light, which is essentially physics, and then adapt it dynamically in the GPU software. And I have a demonstration of it. Now,
Yeah, because that was going to be my question. Like, that's one thing with a still image, but when you're dealing with a series of images, or you're like watching some broadcast where they're changing from different sources, which I guess where you're seeing, you know, how can you even deal with that or regulate that across the different models?
It needs some attention, and there are some ingredients deployed, but I don't believe they're adequate yet. And there's some lively discussion. There's a SMPTE conference coming up, Society of Motion Picture and Television Engineers, in October. So Jim and I are going to be having lots of lively discussions at that.
Cool.
So I'm worried about time. I have a demonstration, and I forget how many slides.
Okay, yeah, good. No, I didn't think you'd be going into so much detail on the slides, but this is great. So time is getting tight.
Okay, well, maybe I should just go to
sure.
demo. Okay.
Well, did you? Yeah, I don't know. Let's see what else you got. Well, yeah, those are the perceptual threshold discussion would be quite a bit. And I see you have a 16-bit half float slide in here.
You can share these.
Yeah, no, I will definitely share the slide.
Maybe that's the solution because of time.
Well, maybe if you want to kind of nutshell, why did you drill to the perceptual threshold slide, the graph? What are you trying to get out there? Why did you put this in the presentation?
Okay, so the axes are kind of the key thing. This down here is logarithmic nits, absolute brightness, as measured by a meter. So you aim a meter at the screen, it tells you nits. And every pixel has a different nits, if it's a real picture. What can we perceive? Well, this is a self-relative tonal distinction. So that says if it's less than these curves, I can't see the difference. My eyes will not pick it up.
That's the perceptual.
If it's above these curves, it is potentially visible. I may not be looking where the error is, but I could see it if under the right circumstances. MPEG-2 is, with no compression, is way up here. 8-bit, a DVI computer screen is way up here. And some of my other slides, you'll see that a lot of other things are way above. So the trick is, can you build a coding pipeline where you can at least stay with these, if not under them? Now, there are multiple of these because it depends on what's happening. If I have sparkling water and it's all glinting, I'm not going to see much tonal distinction. But if it's very smooth and gradually changing, I might see a lot. So it depends on the image, how far I see down. But the lowest one is how much I potentially can see. And if I can stay below that, I'm good.
So the threshold is where the user can perceive an error.
And it really relates to bit depth.
Cool.
Okay, so why don't we break and I have a demo set up.
Good.
So I think I'm over here.
Yeah, crowd
There's a
around.
little screen. And my head is over
Give me this little line of sight over here. I'm going to move the streaming cam over to it.
Good. Okay. Come on. Don't be shy. This is a 5K picture. If you can't see every last picture, you're too far.
You should, if you can't count every pixel.
10 bits RGB, so 30 total, and it's a wider color space than traditional television, somewhere out in the TV. Okay, so I have, this is Linux 6.7, and I have the system monitor here with CPU history. So this little slider over here is down to 88. So that's 2 dual cores with 22. Okay, so I'm gonna tickle this with some various things. So the first thing I'm gonna do is I'm gonna show you a 5K decode with normal amounts of processing. Decoding to 5K. And this will be running at about 29 frames a second. I can't go any faster than that, even though as in a second you'll see, I'm not using the CPUs nearly full. That's how much I was using the processor. Now notice nobody's down at 0. Everybody had work to do. But I'm limited by memory bandwidth, the PCI, and the kernel copy, and those things. Okay, so now this one is a more complex coding structure with more layers and things in it. And what it's going to do is it's going to use more of the CPU. And it'll tell me how fast it went. You see it's not quite as smooth. So that's how much it's using. So it's getting a lot of the processing power applied to it. So now I'm going to, if I give it the password, I'm going to use a nice 9, which is a positive numbers or negative niceness in terms of the priority of the scheduler. So and normally it's 0. The default niceness is 0. So 9 is a negative priority, positive 9. And what we're going to see is that we have a different distribution, and actually you can see the hyper-threading. The 44 that weren't hyper-threaded versus the 44 that were. You see that split? There were two groups there. So this, I think, is nice 10. So it's actually going to move those groups, even though it's only 1 unit. Nice goes from -20 to +20. -20 is the highest priority. +20 is the lowest. And you can watch the smoothness of motion or not. So that was 10, and you can see it's different. Yeah, it's got a bigger spread between the top and the bottom. Nobody's down at 0. Everybody has work to do all the time.
It's keeping the same frame rate.
Well,
Or is it a bit different?
you can see
Yeah,
it's not completely smooth. It's trying to be. If I did the FIFO thing with the whatever those were, cross sync messages, I could maybe fix that. It won't do that if I use the DVS. Okay, see, very different. So that was nice 19. Now I'm going to do nice -19, which is the highest priority that nice scheduler will let me do. Okay, and that's really kind of struggling keeping speed there. And any of you who are close enough can see all that details in all that tiny stuff on the horizon. Yeah, motion blur. You know what that is? The shutter's open and the truck's moving. So again, a different pattern. Okay, so now I'm going to do a chert 50. Chert goes from 1 to 99. It's the range of, and that's, I think it stands for change to real-time scheduling. And chert 50 behaves exactly identical. Oops. Chert 50 behaves exactly identical to chert 1, except occasionally there's some other process that ran afoul of the schedule. That didn't usually happen. So that was just for your benefit. Okay, so now notice that's not very wide, and this is how long the thing runs. That is because the cycles for this update were stolen by my process when I went chert 50. So now I'm going to do chert 99, which is the maximum real-time priority I can give it. That's the highest that the system allows.
Sounds like you're cussing in Russian.
Yeah, yeah, chert 99. Anyway, you can see it's having a big, that's the highest priority I can give it. It's having a big hard time. The reason is there's some lower priority thing like X11 or GL or CL or whatever that I need to be giving cycles to that I'm stealing them all from. Yeah, and it could be starving on cache misses or hyperthread or context switches or I don't know what. And you'll see that this looks very different. That's what that looks like.
It's kind of counterintuitive, isn't it? Because you'd think, yeah, I put it
And,
higher, it should be.
well, 97 it's almost reasonable, so it's somewhere in the very high numbers that the chert affects it. Now these schedulers change with versions of Linux. So chert and nice and all this, you'd have to take new measurements when you do a major upgrade to some other whatever. But these seem to work at least on Ubuntu and here on Scientific Linux, which is of the Red Hat variety. Okay, so let me run this in the script. I can remember everything I'm doing here. Okay, so this is a test chart set that's 16-bit half float, high precision. See that as a smooth gradation there? That's because it's 10 bits. It's actually got more than that. And if I raise or lower the brightness, if you see left or right movement, that's because there is some perception of the lowest bit at 10 bits. At 12, you probably wouldn't see any of that. This is the color gamut. You want to see continuous gradation across all of these. If it's behaving right, and you can see these are pretty good colors. They're outside of the color space for sRGB and Rec 709, but not quite out to the digital cinema space. So we have a series of charts here. These are actually available from Joe Kane and his website if you're interested in them, if you do any work like that. But these actually show up all kinds of interesting stuff on TV sets. You see a lot of things with these test charts. So I'm going to make this smaller. There are a bunch of these chart sets. The first one's at nominal exposure. Then up 3 stops, down 3 stops, up 6, down 6, up 9, down 9, up 12, and then groups of 4. This last one has 4 charts. Up 6, up 12, down 6, down 12. Now a stop is a factor of 2. So this is 64 times nominal. This one is 4096 times nominal. This is 1/64th and 1/4000th of nominal. So I'm going to make it small so it goes quickly. I'm going to drop the exposure after decode. So this went through the codec. And what you see is that the grayscale starts reappearing here. And as it comes down, these bars are going to show gradation. So that's down 6 stops, factor 64. Wow. And I'm going to continue to go down. And then this guy's going to come in, and that's 12 stops, so it's 4,000 times nominal. Okay, so there he is. And now I'll reset, and I'll go the other way. I'm going to increase. This guy is down a factor of 64, 6 stops, so it's going to come up into visibility. I'll make it smaller so it goes a little faster. and then this guy's going to come in, and this is down 4,000. So this one's down 4,000, this one's up 4,000. That's 16 million to 1 difference across that edge. So this white is 16 million times that white.
Are you doing anything on the? I mean, is that just the value that's hitting it would just get clamped on the screen?
Yeah, these guys just
It's not. Yeah.
right. So and well, if I hit reset, you know, it goes back to where it started. So what you've seen is after decode. So all this was in the encoding. After decode, I had 16 million to 1 range of entire pictures. So a 10-bit picture under 16 million. So it's an enormous range. And basically, what the point is that this codec at high efficiency, Blu-ray kinds of bit rates, is way beyond any camera or any display. So the codec doesn't have to limit the system, which is not true today. Today, the codec is limiting the system, even when you go to front. Okay. So these scenes were courtesy of IMAX and Sony, shot with an F-65 camera. So this is a mock-up of the space station. These guys are aliens. You did not see them. And there's gravity on there. This is a 5K. The F-65, let me stop it again. This produces, you can see if I drop the exposure, I have all that extra range on the lights. And similarly, if I look in the shadows over here, I have all that range. So I have, this is a high dynamic range real picture. The F-65 makes an AK Bayer pattern. And what I've done is to downsize that down to 5K and noise reduce and sharpen and all. Now this is a 4K extraction, 4096 by 2160. And I have put around here a bezel to help establish a white reference. And if I were to mess this up and add a lot of red, it goes into here but not into the bezel. So what Jim and I and some other people are exploring is how do you master in this world? How do you understand if you have a good color balance and a good reference, especially in high dynamic range? So this is the one we've been looking at. That's the 5K of it. And lots of detail out there. And this was shot at 60. So this is being, and I think I'm playing it at 30. So I'm playing it at half speed, which is part of why you're seeing the motion blur, because that truck's moving faster than that. Okay, so this is another, this was shot by Society of Cinematographers, and it's called the Camera Assessment Series, and it has a number of interesting features. This is going to judder a little bit because it's at 24. Well, that's normal. At 24, you can't really move the camera this fast. There's also a lot of range here. This is bright outside. This over here, this was lit intentionally behind this guy coming up here so that there's no light on his back. And so this is a stress test. This was photographed as a stress test. Trying to remember the order and when to stop things, but I think I have all the points in here. Okay, so this is another scene, also part of that same test. Again, a stress test. She walks up in shadow, and this is one nit out here because the lights in this display just don't make a good black. But on OLED, we get down to 100th of a nit. So depending on the display, we can check the dark area.
And this is the same as you said, the Blu-ray-ish bit rates?
No, I'm probably higher. I'm intercoding these. I'm not trying to get the lowest bit rate. Now, this is the only light on her face other than a few bluish lights way out here. So that's an interesting, again, another stress test on the scene. Now, there's an interesting question. What do you do about neon? And I can say, well, that should be fully saturated, or I can say that should be pretty much desaturated. You know, and both you can't say which is really right, but there's a kind of an open question about what do you do about really bright colorful things, like a tail light versus a highlight on somebody's forehead.
Well, the neon is pretty hard.
Yeah, I would assume like LED lights in the future, you know, like this street lights now, they have the LEDs, they're a lot brighter. Would be a challenge.
So this is interesting. This was the original camera scene that you saw before, and next to it here, I have a graded scene. That means it went through a color adjustment where the brightness was darkened in the outside a little bit because he's where the action is. And then when he comes around the corner here, you see the ladies outside. This is darker than that. Now you have to be at the right angle. Where I'm sitting is sure. Now so that's been darkened. That's what they call a power window. It's actually a moving region that we're darkening. And then over here, when he comes over here, this is going to be brighter because he's in shadow and he's where the action is now. So he's been brightened up. So what this means is the native from the camera and the adjustments have no bias. Now this is not something understood, and we're actually having a big battle over this because people don't think this is possible. So I'm trying to spread the word. Yes, you can do this. And it was done as a group, so a lot of us participated in this.
So are you saying the information was always there?
Well, what's interesting, let me show you. Okay, so this okay, so this is graded and it's raining. Okay, so there's the noise floor. Okay, and that's what it looks like at nominal. Now, this is interesting. This is different. She has bright red lipstick here, and that's desaturated here. So this change is a different kind of change, and the flames are different. They clipped in the camera, and they've been handled differently over here. So if I drop the exposure, see these flames are different than those flames. So the kind of treatment that's going on here is the kind of treatment that would happen in a full grading session. But normally people would expect some kind of bias, not this neutral behavior like this. Now when it comes up front like this, same kind of deal with the sparkler. So if I drop the exposure, see they put color in here, whereas the camera had that all clipped out.
The one that's graded, was it graded for Rec 709? Or?
No, it was graded on an HDR display. And you can see that the noise floor, like his hat there, they're in the rain. Those are dark hats, black band, but the noise floor was not touched. So the dynamic range was preserved through grading. And if you have a screen that's your reference and it doesn't see the full range, you don't know what you have. Whereas if you make something that's in the same space as the camera original, you do know what you have, and the range makes sense. Both in and beyond. Now, another issue that I mentioned is that it's possible to have different brightnesses of display. So this now looks brighter, but what's happening is I have a neutral density filter here, which is one stop. Maybe you can hold that phone. So, yeah, I got to take it off. So what you can see is this is been knocked down a stop, and what I'm trying to do, I can't make the same brightness here, but I'm trying to get approximately the same appearance. And this is only a matrix difference from that. So we're exploring this issue. I call this single master HDR, so that the GPU processing that's going on, and hopefully as simple as possible, but so that you can get an appearance match, that's a factor of 2. Well, one stop neutral density is a factor of 2. Let me raise it up again so you can see it. So this is twice as bright as that. And when I knock it down, so the whites can't be as white because I've eaten half the light. This is 150 nit max. That's 300 nit max. But otherwise, I'm giving a very similar appearance.
But it's not as simple as just half the brightness. Is that what you're saying?
No.
Yeah.
Well, it takes a complex algorithm because colorfulness is a function of absolute brightness. But there are a lot of other things going on because I can't make the same brightness here that I can make here, but I want the mid-range to appear the same. See, this is just fundamentally different, but I'm trying to get a similar appearance on it. I'll let it play through. So we've done this with high. Well, I got to take it off in the next scene, but you're being awfully helpful. You see this? It's working, despite the fact that that's a factor too. And we have more range that we have to go over. We have to go from maybe 200 to 2,000. We have a lot of range to cover. So this is a challenging adventure. But this is how. But the black is better here. Free improvement to the black.
I'm wondering if that's why I did it or something.
Okay, I think I'll. Let's see. I hit the escape, and then everybody did all the timeouts.
This is the Canon?
Yeah, this is 5D Mark II time lapse.
It's a Mark III, is it?
Mark II. This is Mark II. So this one basically, I just wanted to show that if you look at the colorfulness, see that, and it doesn't change the things in the nominal brightness. It's basically just saying, you know, how much color should there be in the super bright stuff. So I think that's
Good.
Okay.
Hey, thank you very much, Gary.
my pleasure. Thank you.
Thank you for hauling all this stuff.
Yeah.
Not bad.
I'll need at least one person to help them haul it out. So thank you, Gary. Hopefully see you back in a few.
Thank you.
Yeah, I do have the slides. I'll post them up somewhere.
It's got my email address on there if any of you want to.
Yeah, and hopefully I'll send you the call for papers thing for scale. Maybe you just send them the slides, a brief description that should hopefully get you through the door.
Yeah, I don't know how I do this part. But
Well, you
have
can do
to
it in
think
the
about
room. Well, actually, the presentations are broken down into smaller rooms. So you can just bring your gear in and just gather around, folks. I mean, not everybody's going to be able to see it, but, you know, maybe the real interesting folks will elbow their way to the front. So, or you can handle it with after discussion or what have you.
Or get Fry's to sponsor you with some
Yeah.
5K TVs.
Yeah, we can get some bigger 5K screens. Anything's possible if we have enough time. So
when's the show?
it's in March.
Yeah, so by then I might be able to get a bigger screen. I've been having trouble finding a good enough screen that gets big, so I've been kind of sticking with what works.
Yeah, no, I mean this is the perfect crowd for this.
Do you lose brightness range of projectors?
We can measure it.
So we'll
but
have somebody.
the black's not very good. The right side real bright.
So see you next month.
You know these video
If
walls,
there's
they
extra
get really
sandwiches or
bright.
whatever,
So
go feel free
I
to
think
take
if
them.
you want to be big, that's probably
You're welcome. Hey, thank you for showing up. Thanks to everybody out there in internet land. Shows up.